So I would like to thank the organizers for presenting this poster in Reuven Opher Challenges of New Physics in Space. So we will be talking about static universe. So in GR, these solutions are well known. Even Einstein himself worked with this. But also in the beginning they already noticed that the solution is not stable. It is possible to obtain stable solution in GR if it's considered two fluids and with opposite energy density. The energy densities must have opposite sign. Quadratic gravity is interesting because it can be thought as a generalized gravity for very strong fields. So we have GR, and alpha and beta are modifications in GR due to very intense gravitational fields. So this theory is not new. It began with Hermann Weyl in 1918. And after that, apparently the first after Weyl was Buchdahl in 1962. And in 1980, Starobinsky proposed his inflationary model based in this quadratic gravity, specifically just the R² part. Okay, recently Starobinsky inflation is being confirmed by the latest CMBR measurements by the Planck collaboration. So after the 60s, many people worked with quadratic gravity. So in contrast to general relativity, it is possible to obtain static solution for quadratic gravity with only one fluid and both for positive and negative spatial curvature. So we first addressed isotropic case because the solution occurs with isotropic space-time, and the solution is written here. So we have A here is logarithmic of the scale factor. Scale factor we use calligraphic R as written here. And the solution is given for this particular scale factor and this particular energy density written here. So here we have beta, which is written here in the Lagrangian. W is the equation of state parameter for P is equal to W rho. And K is the curvature, which is either +1, -1. For zero spatial curvature, there is no static solution. So what's the difference here is that there is a possibility for static universe for negative curvature also. In GR, this is not possible. So negative curvature with positive energy density, which is written here. So it's possible to have positive energy density, static universe with negative curvature, but it's not stable. And here we also write down the linearized modes of the quadratic gravity. So quadratic gravity has the spin 2 massless field, which is the same in GR, a massive scalar field, which is the scalaron, the scalar degree of freedom, and a ghost spin 2 field with this mass given here. So stability of Minkowski space requires beta positive and alpha negative. So linearization around the static solution gives us these linearized frequencies here for the isotropic case. So there is static solution for positive and negative values, and there's region of stability for negative curvature. There it's only unstable. Stability with negative curvature can be achieved for negative energy density, which is not so physically motivated. We don't believe that. So for positive curvature, there's range of interval approximately given here for the equation of state parameter in which we have stability. Stability can also occur with the presence of the tachyons here. So if Minkowski space is unstable, even though for is unstable Minkowski space, there is possibility of stable positive curvature static solution. So here's a grid of initial conditions, and here in the center is the static solution, and here is the gray points. Here are the region of our initial conditions which stay near here. So it's visualization of stable basin. Black points here are initial conditions in H, and the difference in A is the logarithmic of scale factor. So AS is the static solution, which is written here. So there's deviation from static solution. Black points here are initial conditions which converge to the singularity. And black points here are solutions initial conditions which asymptote the scalar behavior near Minkowski space. So since here is isotropic case, only the isotropic case, the frequency, there's only one frequency for the scalar, which is this one, this frequency. Okay, now we see if this system is also stable if there is shear, and which we also checked shear can be introduced if we go to the non-isotropic generalization of the spatially positive curvature case, which is given by Bianchi-9 homogeneous Bianchi-9 3 algebra. Okay, so details are in our work which we did here. So shear is introduced, and then we have these additional frequencies here, eigenvalues. So besides these eigenvalues for isotropic case, there are these other ones here. So there is also here region of stability. So the details of the region of stability is in our work, and here we just present also stable basin. So here in the center here is the shear variables. So in the center there is no shear. So the center is the static solution, this one. And for initial conditions near, we have oscillations. And black points here is singularity. We stress here that singularity, we took special care that singularity is characterized by curvature invariance. So real physical singularity. And gray points here are solutions which stay near the static solution. So in alpha we choose beta positive. So positive beta is by choice interesting because it can include the inflationary Rusmaykin-Starobinsky solution, which is this one. So there is possibility of inflation for positive beta. Here also we have positive beta written here. And here we put both for alpha positive. So alpha is the other parameter in the Lagrangian. So for our positive alpha we have tachyon. The ghost mode is tachyonic. So in this plot here, in this basin, the ghost mode is tachyonic, while in panel B here the ghost mode is not tachyonic. So in panel B we have only singularity and oscillations, and in panel B there's possibility of stable region of oscillations, and black points are singularity, and there are white points also. White points also are both scaleron and linear ghost oscillatory modes. So the scaleron and the ghost mode are present here in this white points which are white, so initial conditions which converge to this asymptotically flat Minkowski space for a very asymptotic time. They can oscillatory modes. So I thank you again, the organizers, for the opportunity, and this is my personal contribution and to celebrate in homage to Opher. Thank you very much.